One of the things that you're going to encounter a lot in this class is the natural exponential base e. So what exactly is e? So e tends to appear a lot in areas in biology and in business. So basically what this means is that if you were to look at this expression 1 plus 1 over n to the power of n, as n gets large, so if you start putting a lot of different values of n, if you plug in a whole bunch of n values, n equals 1, n equals 2, n equals 3, n equals 100, n equals 1,000, what this happens is that as n gets bigger, this expression approaches something. So this approaches a particular number, and that number is 2.71828 and then some other things. And actually what we end up choosing this to be is the letter E. So you can see this letter E is in your calculator. It's very similar to pi. So if you remember, pi appears in geometry and is equal to 3.14 approximately. In this case, E is 2.71. And the way that we really found this out, and probably you're wondering where exactly is this expression coming from? Well, it's coming basically from this particular expression, from this formula, and that formula is compound interest. So this interest formula is basically, you don't need to memorize this formula. I will give you this formula, but it's A equals P 1 plus R over N to the power of NT. And let me tell you a little bit of what this is. This A is going to represent my new balance. Okay? So what is the new balance when P is what we call a principal? So imagine that the principal is the amount of money that I'm investing, or the amount of money that I'm putting down for a home, okay, or whatever. R is going to be my rate as a decimal. Okay, not as a percent. And I'll put that in red, not percent, because I will mess it up. Not percent. Okay, so as a decimal, so that's basic. Usually we call this the APR, okay, the annual percentage rate. So that's going to be my R. My N here is the number of compoundings. And basically what compoundings are is how many times am I adding on to the already accrued interest. So how much am I compounding it? So am I adding interest once a year? So every year, yearly? Am I adding interest every month? Am I adding interest every day? So what exactly is it? So N is the number of compoundings. And T is just time. Okay. Now number of compoundings, let me just give you some examples. N equals 1. This is yearly. That means I only add interest once a year. N equals 2. This is semi-annual. Okay. N equals 4. This is quarterly. Okay. Can you imagine what monthly is? N equals 12 is monthly. Daily? Well, that's N equals 365 days. So that's going to be daily. Okay, and so on and so forth. Okay, so this is the formula that we have. Now, as n gets larger and larger and larger, remember that this expression, which is basically this particular part, when the interest rate is 1, tends to approach e. So the way that this happened was that we assumed that, let's say we put in $1 as our P at 100% interest rate, which never happens, compounded yearly. And we wanted to see where exactly this went, and what happened is that we can actually rewrite this formula as A equals PERT. And this formula is only used if you're compounding interest continuously. Now you might be thinking, well, how am I going to accrue interest continuously? Well, maybe not with money, but in biology, bacteria tends to increase continuously. So this formula actually is very powerful in biology when you're trying to model how much bacteria is going to be in a particular petri dish after a certain amount of years. Okay, especially if you're doing research and you want to find some cure and you want to figure out all of that. So It has a lot of really great things. So right before I go to the next problem, I do want to say that we can express f of x equals e to the x. And e to the x, actually, well, if e is 2.71, well, this e to the x actually is going to be exponential growth. It still has an asymptote. It still has an x-intercept. When I plug in 1, I'm going to get whatever e is. When I plug in -1, I'm going to get 1 over e, whatever 1 over e is. So I still can use the same exact things as I did before, just by plugging in e. So yeah, so let's do one problem. And this is my word problem. So suppose that $12,000 is invested in a savings account. If the interest rate is 4%, how much money will be in the account in 12 years if compounded quarterly, monthly, and continuously? Okay, so whenever you see something that looks like this, you know I have to use that formula, and that formula will be given to you. So I will have to be using the formula A is equal to P 1 plus R over N to the power of NT. Okay, so this is the formula that I have to use. Okay, so A, so how much money, so that's how much I'm gonna have to have in the end. So how much will be in the account? So that's talking about A. Okay, so P is the principal. How much did I put in the very beginning? Well, I put in 12,000. That's how much I put in the very, very beginning. Now this one is just there, plus R. Remember, R, we do not want it as a percent. We got to convert it to a decimal. 4%, remember, we can drop the percentage sign and move the decimal point over 2 places. So this is going to be 0.04. 0.04 divided by N. N is the number of compoundings. Since it's quarterly compounding, quarterly is 4 times a year. All to the power of 4 times t. T in this case, how many years? For 12 years. And all you got to do is put it in your calculator. This is where the biggest test is. Make sure that, since most of you guys are using different calculators, make sure that you really practice it. And if you are still having problems, please come see me, or I can do a video with the type of calculator that you have. I might put a video later using the TI-36 so I can show you what it is. So what I ended up getting was 19,346 with about 71 cents. Okay, so that's how much I got. All right, and you mainly want to round to 2 decimal places because it doesn't make sense for you to have more. 71 cents is correct. Okay, so that's what you have there. Now, what about monthly? What about if I was continuously being added? You continuously add interest every month. Well, everything is going to be the same. A is equal to 12,000. 1 plus 0.04. The interest rate hasn't changed. Now, this time is going to be divided by 12. And then it's still 12 times 12, because 12 is the number of compoundings. 12 is the years. Okay, so everything is going to be exactly the same. So 12,000, 1 plus 0.04 divided by 12, raised to the power of 12 times 12. And what I'm going to get is 19,377.42. All right. So notice that the differences between adding interest 4 times a year compared to every month, you know, look at the money. It's not really that significant. For 12 years, it's not significant because if you think about it, if you really want to make something significant, you don't want to leave the money there for many more years. What you really want to change is your interest rate. You know, your interest rate at 4% is not really, it's only going to do so much. And so if you continuously add interest, well, let's see what happens. What happens when I continuously add it every single second or millisecond or whatever that is? Let's see how that will change it. Well, because it's continuously compounded, we're not going to use this formula. We're going to use the PERT formula. A equals PERT. Okay, so that helps you remember it. A equals P-E-R-T. So this is going to be 12,000. E to the power of 0.04, and then t is 12. Now, your E, if you're using the TI-36 for TI-36, if you look at the first column, where you're going to see the second button, then you're going to see ln log. Right below that, the third button, you're going to see E and then a box. You're going to press that button to get this E. Okay, so you're going to put 12,000, then that E to the power of 0.04 times 12. And what you're going to get is 19,392 with 89 cents. So compare it. Compare all of this. See that how it didn't quite make that much of a difference, only a couple dollars. So you really want to change your interest rate when it comes to these types of problems. Okay, so hopefully this was good enough. We will do more complicated problems where you actually want to figure out how long it takes for you to have a certain amount, but we need to do logarithms first before we can do those types of problems.